does altering concentration influence the rate of the acid-base reaction between hydrochloric acid and sodium hydroxide when becoming sodium chloride and water? Chemical reactions are a fundamental process crucial in every aspect imaginable, from respiration and digestion to cooking and cleaning, and distributing energy and power to basically everything. Chemical reactions are merely the process in which one or more substances transform into another through chemical means, whether by particles coming together, disbanding, or both. We describe how fast a chemical reaction occurs using the term rate of reaction, the rate at which particles of a reactant collide with one another at the minimum speed required to break existing bonds, and the rate which products form from that. Several factors alter rate of reaction, one of which is concentration, the one explored in this video. Concentration is the amount of substance in a defined space. The concentration of a substance is the quantity of solute present in a given quantity of solution. To showcase the effects of concentration on rate of reaction, we will be using the acid-base reaction between hydrochloric acid and sodium hydroxide. An acid-base reaction is also known as a neutralization reaction, as the extremity of both pH levels combat one another, leaving the products neutralized and simultaneously undergoing double displacement. When you have an acid and a base, they combine to form salt and water. The ionic bonds connecting sodium, oxygen, and hydrogen together to create sodium hydroxide and the covalent bonds pairing hydrogen and chlorine to form hydrochloric acid break apart due to the presence of sufficient activation energy. This causes the hydrogen from the hydrochloric acid to switch places with the metal sodium. This now means that sodium and chlorine are paired together, and the hydrogen and hydroxide components are combined, producing the salt compound sodium chloride, which is table salt, and water. As we can see, no matter is destroyed nor created, obeying the laws of the rearrangement and conservation of atoms in a reaction. Concentration is extremely influential in not just the rate of reaction, but also the extent of the reaction, meaning not all reactants are entirely consumed during the reaction, resulting in an unreacted excess. Modifying acid concentration either increases or decreases the rate of reaction, also referred to as the frequency of collisions between particles. If you decrease the concentration of the acid, there are fewer acid molecules present, hence the chances of acid-base collisions are reduced, resulting in a lower reaction rate. However, if you were to increase the concentration of the acid, the rate of reaction would also increase, as there are more acid molecules available to react with base molecules, leading to a higher frequency of collisions. It's important to note that if the temperature of the substance stays constant, then all particles will have the same average kinetic energy, meaning the proportion or ratio of collisions each second will also stay the same. If there is an increase in concentration, meaning you add more of a particular substance, there are more particles squeezed into the same volume or space as before, resulting in more opportunities for collisions between particles to occur per second. So, statistically, more successful collisions are bound to happen, which increases collision frequency and therefore the reaction occurs faster. This concept is known as collision theory, the theory that for all chemical reactions to occur that particles must adhere to a certain checklist which states, particles must collide with one another in order for a reaction to occur. Colliding doesn't necessarily mean a reaction will occur, but collision is a prerequisite for chemical reactions. Another factor is activation energy, the minimum energy or speed required for an existing bond to break upon collision, sometimes referred to as an energy barrier that needs to be broken to allow a reaction to commence. When the required activation energy is met, a transition state is formed, meaning all old bonds are partially broken and new bonds are formed. The transition state is the highest point of energy reached during the reaction just before the products form. Varying reactions need different amounts of activation energy. Higher activation energy results in slower rate of reaction, and a lower activation energy corresponds to faster reaction rates. It is also important to know that activation energy is independent and unaltered by concentration, but they still correlate. The last factor is the particle's orientation. Even if two particles collide at the right speed, their bonds may not break if they do not collide at the right angle. So, to reiterate, the increase of concentration leads to the frequency of collision between particles to rise. Statistically, we can assume the number of successful collisions grows, ultimately meaning more energy is produced, allowing the energy barrier or activation energy to be overcome, therefore causing the reaction to occur faster. We can apply this to the acid-base reaction we've been discussing between hydrochloric acid and sodium hydroxide when becoming sodium chloride and water, as when either reactant, acid or base, increases, the rate of reaction increases with it for the reasons stated and explained throughout the video.